So welcome back, everybody, to this main room for the wrap-up. I hope you had a very fruitful discussion. Now I will ask to each moderator to share with the audience the main conclusions that you have reached in your rooms. So we'll start with room number 1, Alejandro Franco. If you can share the conclusions with the audience, please.
Yes, I don't know if you will show this data miner results or not, or I should comment orally.
I don't know. I don't know if they are ready, Iñaki.
Normally they should be shown. That was told to me.
The idea is, I don't know if they are already, Iñaki can share, or I don't know, Iñaki or Maria or somebody from the TheText team can show these results.
Not yet. We are working on that.
Okay.
Okay, I think now, perfect. So, well, in this AI group, so we discuss five topics. So, which are the first one is which are the pain points of bottlenecks in implementing AI for data analysis. Well, as you can see here, so yeah, people highlights the lack of data standards. This is very important because when you will develop a machine learning model, which is a subclass of AI, so you will need to train properly the machine learning model, and for that you need clean data, right? I would say this is a very, very important topic. And also the need of very large data sets, right? This is not what we were discussing in the group, is that this is not systematically true, okay? So I show for an example of work that we have performed where we demonstrate that we have a data set of 100 experimental points. It was possible to derive a machine learning model with accuracies higher than 80% for predicting electroporosity as function of processing conditions, manufacturing conditions, right? We can move maybe for the next one. Which are the main expectations regarding the AI for data analysis? So you see the majority of people, they think that it can be very useful for reducing the amount of experimental efforts. And this is true because machine learning models, their power is that they can deal with multidimensional data sets. They are very powerful to unravel interdependencies between in data sets where you have multiple inputs and multiple outputs, right? This is a traditional problem for experimentalists, right? You are collecting a lot of data, you have a lot of inputs you play with, you will have a lot of outputs. And this is the power of machine learning, is correlating these parameters all together and discovering with the ones that are really controlling the overall behavior of the system, in this case, the manufacturing process chain in particular. We can move to next. So what you are doing to reach your goals using AI for data analysis. So many people actually highlight that they are using in-house, I mean, they are doing in-house training. And what we were commenting, this is particularly true for many of us doing computational modeling on batteries. Now AI is blooming, right? It's a blooming field. So there are plenty of very interesting techniques that are emerging to deal with different type of problems, such as, for example, lifetime prediction for battery aging and so on and so forth. And well, this push many people to learn about the techniques, but also something that we have discussed is that it's very important to keep an eye on computational science tricks, because, you know, when DFT techniques, density functional theory calculations emerge, so many people, they were using DFT as a black box, right? But then to make reliable computations and reliable predictions, you really need to know a little bit what is behind, right? And then the take-home message here is that yes, machine learning can be very powerful, but also please keep an eye on what in the hypothesis behind, because in a machine learning model, you can have hyperparameters, I mean, parameters that you need to adjust empirically, right, to make the prediction in a correct way. And you need to be, you know, aware about these limitations, right? The machine learning presents as well. Okay, so the other question is, what is machine learning? So this was a test question because in literature also we can find a confusion between artificial intelligence and machine learning. So we see majority of people, they say a type of artificial intelligence, and this is true. Machine learning is a subfield of artificial intelligence. Even if in a publication you write artificial intelligence, and this is very fancy, right? It's very eye-catching. Be aware that machine learning is a subclass, right? It's not really artificial intelligence. It's more, we could think a machine learning model like a a technique based on advanced statistical methods, right? It's nothing more than mathematics and advanced statistical methods, right? They are very powerful, once again, to unreveal parameter interdependencies in multidimensional data sets. A machine learning model is a computer program that, okay, this is also a test question, so does not understand anything what is written here, and also predicts numerical outputs from inputs. Definitely, you can have a machine learning model to make numerical predictions, such as capacity retention, lifetime, or the tortuosity of an electrode as function of manufacturing parameters. I show an example in that direction in the group. But also it does not understand anything what is written here. So I show an example of application of machine learning for text mining, you know, automatic extraction of battery data from scientific publications. To do this, you need to train a neural network, which is a type of machine learning model that will be able which is able to detect entities and the relation between entities, right? Even though this model can be very useful to extract data, it will not understand the meaning of this data, right? Then if you don't do a proper training of this neural network, so you will extract from publications whatever, right? And once again, this calls for standardization on the way that we report data, battery data in scientific publications. If all of us, we agree to report battery data in a standardized way in scientific publications, then it will be possible to imagine in the future machine learning models that can exploit the data available in scientific publications to make battery optimization, manufacturing process optimization, and so on and so forth. So I think that's all for the discussions in this group. Thank you very much once again to CDTech for the kind invitation. It was a very exciting workshop. Thank you.
Thank you to you for joining this workshop. Now let's move to the second room. Arno, please.
Yes, yeah, thank you very much for preparing the results. Yeah, first of all, what are the pain points or bottlenecks for digitalization in the battery manufacturing? And the main point was to have the right sensors. So that means to get all the data in the different process steps, which are necessary to have a good simulation, but also have good data, then maybe also statistically based data analysis, but also to have a control of the machines. But besides that, I think that's what we can also provide by such projects like de facto is a lack of knowledge. And also what was interesting is non-adaptive equipment. That means even if we have a good knowledge and if we could control the machines, and the machines are not able to be adjusted in the right way. Then maybe the next one. But money and time is not the biggest issue. Yeah, that's also interesting. So now we are coming to the expectations regarding digitalization. And the main point or the most important point is quality control. And that means we discussed shortly not quality control only of the final cell, that's more for the intermediate products. And because if we have a good control at each process step, then we have a really high good rate at the end. That means most of the cells, or hopefully 100% of the cells, are in spec. Besides that, we can control the different production stages or process steps, and by that can have a cost optimization, but also minimizing the scrap and increasing the quality like before. And besides that, it's also speed up the process and reducing manufacturing time, speed up the process. I think it was maybe not so clear what it means, but it can also be, you know, the designing process. That means factory planning can be speeded up by digitalization a lot. Yeah. Then maybe the next one. The next question was what certain people are doing to reach the goals. I think it was the same question like in the group before. but now for battery manufacturing, and also like shown by Alexandro, it's in-house training is the most important one. So getting knowledge to the people, I think it's really important training, and this is maybe something we can also increase in Europe to have a really well-skilled people here in the big companies. And how to do that? So that means we can first of all maybe have to recruit a specialist if we don't have one, but we need somebody who is responsible for the digitalization. And then the question is, if we have experts in-house, that means especially in bigger companies, maybe we have that. Otherwise, we have to have a partnership with a specialized company or also research institution. I think also especially research institutions can help regarding the digitalization. And then we have two more technical questions. So one was regarding which process steps are most difficult to simulate. So it's a little bit equally distributed, but it seems to be, and I think that's also my opinion, the formation is very difficult to simulate, especially regarding what is chemistry inside the cell, SEI build up and so on during formation, and its effect then on the lifetime and the cycling behavior of the cell. And besides then, also electrolyte filling seems to be still difficult. But as we have seen, that's something also what is simulated in de facto. And then what is based on particle scale is the mixing and dispersing of the particles, especially I think the conductive additives, how they are distributed is really not easy to simulate if they are in the nanoscale. And but they are really decisive for the later battery performance. And then it's electrode coating and drying, what is still difficult, and calendaring and cell stack is not so critical. And then the last but not least, regarding, it's a not new question now, but it looks similar. No, this is a new question, yeah. So here we have the question where it is most important or most critical to have an intelligent control system. So what helps us most? And the winner is the electrode coating and drying. And this is, I think, it's nice because this is really the step where we have the most scrap usually, and producing scrap. So that is in the moment most expensive regarding that. So it's really important to have a good control system for this process step. Then afterwards, there's the formation here. I think it's from the controlling point of view, I would say not so sensitive because temperature and electric parameters are more easy to control, but you have to control them, but it's a lot of cells. Sorry, there's one, please mute. And so calendaring is important here to the opinion of the people, and also the electrode slurry production. I think electrode slurry production should be more important to control than the calendaring. Okay. So that's from my side. Thank you very much, and also for everybody who was organizing it. I have to drink something.
Thank you very much, Arno. So let's move to the third room. Arnold, please.
Yeah, so the answers to the first three questions had many similarities to the other sessions. Again, what are the pain points or bottlenecks in digitalization of the battery design? I mean, here it was obvious that the parameterization is the biggest issue. I mean, the number of input parameters and the necessity of cell parameterization, we consider this basically the same question. So there is the biggest need of doing something. And this is something we're also working on, since I think this is a point where we can, by combining data-driven methods and physics-based models, we can get the more automated way of doing the parameterization established. We are doing this, for example, in satellite applications already. And I think there we are on a good way to go in that direction. So then to the next question. What I was surprised with, that the model accuracy was obviously not that important. At least it was only 29%. So this is, for me, somebody who's taking care to build very consistent and good models. A little bit surprising. So the next question was, which are the main expectations from regarding digitalization and battery design? Here it was obvious that enhancing of the battery performance is the biggest bottleneck, the biggest issue. Reduced time to market. I was a little bit surprised that this is not really an issue, but then on a second thought, it's clear that if you think on automotive applications, it's obviously that battery performance is the one thing which really has to be optimized. If you then take into account that also optimal design and better quality products is going in the same direction, this is then compared to costs and reduced time to market, certainly the most important issue. The next question. What are you doing to reach your goals using a digital approach in battery design? Here again is the same as in Arno's session, namely what you're doing is a combination of in-house training and a partnership with a specialized company. I think this is the most rational way to do. And of course, you need specialists. So first you need to recruit some specialists, which you then can use in in-house training. And then for a long-term strategy, it makes, of course, a lot of sense to align with an external partner, be it a company or some research institution, to get the best out of this digitalization techniques. It's obvious that the in-house department is only something which for the big OEMs is a solution. So I think in-house training and a partnership with specialized companies doing actually the same thing. Then the more technical questions. Here I have the same experience again as Arno. In my first specialized question, which aspect of the battery do you want to improve by digital techniques? There was basically an equal distribution, which shows that the audience knows that you have to improve everything to get a good battery. And then if you do, then it doesn't really make big sense to distinguish between the importance. So I think the answer is that you have to optimize everything together to get a good battery and at the end a good pack design. So this is a sign for the competence of the people in my session. So the last question. The main technical focus in digital design. So the biggest was, and this was actually for me surprising, that attendants choose increased lifetime under high load conditions. And I was explaining this as at variance to just increasing power density. I mean, of course, if you have a given lifetime for a battery, which you say you have the goal that your battery has to live for 15 years, then you have to limit the power density in some way. So you increase the power density so much that you can guarantee that under the normal conditions, the battery is living that long. But then if you have, for example, power tools or heavy load applications, then you have no choice. You have to get the highest power density as possible. And then the next most important step then is you have to increase the lifetime by choosing the right design. And this design can, of course, best optimized by using digitalization techniques. And I was also positively surprised that people develop advanced adaptive operating protocols for special purpose applications. And here I explained that what I meant was that over a lifetime of a battery, the situation or the condition, the state of health of the battery is changing, and therefore you have to adapt the operating strategy. And if you then have very dedicated applications, then pure experience really doesn't help you how to change your strategies. And then using the same techniques which you have used to design your battery can, of course, also be applied to develop the advanced operating protocols. So I think this is basically something where I would not like to take the things apart. So design and control have to be thought together. And if you have the proper design tools, you of course can use the same tools to to do a good control. And if you then use mathematical operations, as the one David Howell will probably explain in the model reduction techniques, then you can also use more advanced physics-based models to do the control. For example, also to evaluate the state of health for battery for second life applications. Yeah, this was my sessions again. Yeah, thank you for inviting me to do the moderator, to be moderator here, and it was very interesting for me to see all the other projects in the EU context. So thanks again.
Thank you very much, Arnob. So let's jump to the last room. David, you can share the conclusions of your room.
I cannot hear something.
Now we hear you, David.
Okay, great. Yeah, I wasn't allowed to unmute myself. Okay, well, first of all, thanks again for the invitation to be part of this. It's been a very interesting meeting. So just to quickly touch on the questions that we discussed, the first one was about the pain points and bottlenecks in battery control. And I think similar to what we've just heard from Professor Latz and from others, the top ones were the difficulty of model parameterization and validation difficulty, and then also some overlap with Professor Franco on lack of good data. So this is no surprise. I think this is very much saying the same story as what we've seen from other people as well. I will just say one thing about validation. My own experience with battery controls and application-oriented modeling is that it can be quite difficult to show the benefit in the real world, and that's this validation point, I think, is a key open area where some large projects could make a difference by showing over 3, 4, 5 years that there's an actual benefit in doing this stuff. Okay, next one, please. So the next question was, what are the main expectations or goals or priorities regarding digitalization of battery control? So here, perhaps slightly different to what Professor Latz was just saying, actually lifetime prediction and extension came out as a key requirement, as a priority, and then fast charging as a second one. So I guess this is not very surprising. I think these are obviously topics that are hot topics at the moment, and there's lots of literature on these topics. Some of the other things that came out, so interestingly, balancing systems came out as less important, perhaps because we think that that's kind of a solved problem, maybe. Grid storage optimization, less important. I'm not quite sure why, perhaps because we had more automotive people in the room than grid people. But the other topics that we discussed were improving performance and safety range, and model characterization. So here I think we're seeing a slightly different set of goals compared to the battery design breakout room, which is interesting. Okay, the next one, please. I think here we're seeing a very similar story to the other breakout sessions. So what are you doing to reach your goals? Most people in-house training or in-house department. Some of the people were university researchers doing PhDs, doing in-depth study. So this message is not very surprising, very similar to the other messages. Next one, please. So now we have 2 more technical questions. So the first question I thought I would ask is, should we apply battery control and estimation techniques or models mainly at the pack level, by which I would include the container level if it's a grid storage system, or at the module level, or the rack level, you might say, or at the cell level? And by cell level, it could be an individual cell or a bunch of cells connected in parallel. And what I thought was interesting here was that the majority of people said at the cell level. And I guess a lot of the academic literature on this stuff is at the cell level, because you start at that level and keep it simple. But actually, my personal feeling on this is that you probably want to do it at the module level, because it's a compromise, especially in a large scale system like a grid storage system. The cell level is going to be quite difficult. You may not even have access to all of the cell level information. And the pack level may be too coarse-grained. And just to throw in one other thought, it may depend how many current sensors you have and what the electrical connection topology of the system is, because in the end, Coulomb counting is what underpins state of charge estimation, and then that underpins state of health estimation. And you can only do Coulomb counting for each current sensor that you have. So if you only have one current sensor, you can only really do one Coulomb count estimate. Okay, next question, please. So what are the most important remaining issues for research on battery control? I thought I would sneakily get some wisdom from the crowds to help guide my thinking as an academic for the next few years. So the priority here was demonstration of the improvements of performance in life, which I think is tells a similar story to what I was saying right at the beginning about the need to show that this advanced control, advanced modeling techniques can make a real impact. So we need projects which really demonstrate this. Second one, almost equally important, is parameterization and characterization techniques, which again is very similar to what previous people have spoken about already. I think these two things go hand in hand. If you want to demonstrate that your model makes a real difference, you need to first parameterize it correctly. So these are kind of flip side of the same thing. And then slightly less important, dealing with new chemistries and model order reduction techniques. So that's a summary of our discussion. We had a few other discussions about Second Life and about how to characterize and control cells for Second Life. But it's been very interesting, and I just want to say thanks again for including me.
Thank you very much, David, and thank you to all the moderators for sharing the conclusions of the different rooms. So now we are getting closer to the end. I apologize because we have a delay of almost 20 minutes. I hope that you all enjoyed the workshop as much as I did. I think they were a very interesting discussion for everybody. I don't want to end up the session without saying thank you to all the attendees for joining this workshop. And for sure, a big thank you to all the speakers. It was a pleasure for us to have you on board. If you want, you can fulfill this satisfaction survey using the menti.com program. And just to finish, maybe we can all turn on our cameras to make a capture, and we can use this in the social media, if you agree. And with this, I just will finalize the session. Thank you very much to everybody.